Hey everyone, in this video I will show the strategy that one can use to prove the following two statements. Let r be in the open interval between 0 and 1. We want to prove the limit as n approaches to infinity of r raised to the n is equal to 0. And the next item we want to prove is if we let r be in the open interval between -1 and 0, we want to make use of a to prove that the limit as n approaches to infinity of r raised to the n is equal to 0 as well. Now, these kind of statements would likely appear in an advanced calculus course while discussing convergence sequences or limits of sequences. But before we begin, I will briefly talk about the definition we will work with to present a formal proof for both items. Recall that the Epsilon-N definition of a convergence sequence, which states that the limit as n approaches to infinity of a sequence A sub n is equal to L, where L is a real number, provided that for every epsilon greater than 0, there exists an n, a natural number n, such that for every little n in the natural numbers, if n is greater than or equal to n, then the distance between the sequence and the limit of the sequence is less than epsilon. Now, it is important to note the order of the quantifiers in this definition. Notice we are given an epsilon, so the n that must be determined may depend on a positive number epsilon. So now that we have our working definition, we can begin looking for an appropriate natural number n. The way we're going to do that is by using the consequent of our implication to get back to the antecedent. So we're starting with our inequality and then eventually getting back to this. And so what we'll do here is we're going to answer item A and could do some side work to get to the n that we were looking for. So we consider the inequality r raised to the n minus 0. Notice that this is our sequence that we're working with, and this is the limit of our sequence. So we can simplify this by getting rid of the 0. And we can further simplify this. We can get rid of these absolute value signs because notice that r is in between 0 and 1, a positive number. Our n from the definition is also a positive number, so together they'll make a positive number. The next step we want to take is to bring this n down from the exponent part of r. And to do that, we could take the natural log on both sides of the inequality. The next step we want to take is to get this n on the greater than side. And to do this, we will divide both sides by 1 over n. And we can bring over this ln of epsilon over to the left-hand side. Now, notice we do have the n on the right-hand side, but it's not in the form that we want it in. We want it to be we don't want it to be a fraction. So what we could do to bring the denominator over to the numerator is take the reciprocal, and we could do that by raising both the left-hand side and the right-hand side of the exponent of the inequality by -1. And you'll notice that the numerator becomes the denominator and the denominator becomes the numerator. And now we can make it resemble our definition by switching the inequality, as long as the constant of the inequality on that side stays the same. So we get now a word of warning. We might at this point decide this is the n that we were so tirelessly looking for. But notice, ln of epsilon and ln of r may not be a natural number. Either one of them might not be a natural number, let alone the division between the two values. So for it to be a natural number, we can first force it to be an integer by using the greatest integer function. Now let me quickly discuss what the greatest integer function does and the notation commonly used to represent it. Notice here we have three ways in which we can write the function. We have int of x, we have the L-shaped bracket notation, and I've also seen the double bracket notation. As a preference, I'll use the first option. And we can define the int of x as follows. The int of x, where x is a real number, is the largest integer that is less than or equal to x. So let's take some examples to see what this actually means. If we examine a number line with the integers and take x to be 1/2, for example, where 1/2 is right here. The largest integer less than 1/2, so going in that direction, is 0. So this is 0. If we take -1.4, for example, which is somewhere around here, the greatest integer less than -1.4 is -2. And the last example we have is 2, like if we take x to be 2. Since 2 is already an integer, applying the x will only produce 2. Now that we somewhat understand the greatest integer function, let's use it to our advantage. Recall that our initial choice of big N up to this point was the natural log of epsilon divided by the natural log of r. Let's plug n into the greatest integer function and make this our new choice of n. Before I do that, I'm going to label this n with a subscript 0 to represent our initial choice of n. And then I will continue using the subscript style to represent each new n that we make. So notice that this is an improvement because we have ensured that n is not a decimal number at this point. There is a drawback, however. Recall that the greatest integer function can output negative integers and 0, as we have seen in our examples. Both negative integers and 0 present a problem as they are not a natural number. And natural numbers are defined as a set of positive integers strictly greater than 0, or simply 1, 2, 3, 4, and so on. Let's first address the negative integer issues. Looking at our new choice of n, suppose that we do get a negative value after evaluating the greatest integer function. Remember, if we raise a negative value to the second power, the result is positive. For example, if we take -1, raise it to the second power, we obtain 1. Let's apply this fact to our new choice of n. Now we're getting close to the end that we are seeking, but we should address the next flaw, that the greatest integer function can potentially produce a 0. So let's say we do find that this new n gives us a 0 after the greatest integer function and the second power are computed. Since 0 is not a natural number, to fix this, we could just add 1 to our choice of big N. So we just copy down what we have here. And now we're in a position to write our proof for item A. So let's begin our proof. We can start by first introducing the epsilon. So let epsilon greater than 0 be given. Now we use the big N we found in our side work to establish our choice of big N in our proof. Define n big N to be We then want to introduce the last clause of the Epsilon-N definition, which states that for all natural numbers little n, little n is greater than or equal to big N. Since n is associated with the universal statement, we have no choice over it. So we can say let little n be greater than big N be arbitrarily chosen. Now we just have to use all this information to prove the inequality. The distance between the sequence and the limit of the sequence is less than epsilon. So let's write then the distance between the sequence and the limit of the sequence, which is equal to r raised to the n minus 0 is equal to r raised to the n. And we get rid of the absolute value bars because we found that the quantity inside of the absolute value bars was positive. And now we can use what we know about little n to establish that r raised to the n is less than epsilon, but we're going to use that at the conclusion of our proof. So we notice that we can claim that the big N that we chose is certainly greater than the natural log of epsilon divided by the natural log of r. That is, so this is just a comment. You don't have to include this in your proof. So the int and this is certainly greater than ln of epsilon. But why? Notice that here on the left-hand side of the inequality, this is strictly a positive number, while on the right-hand side, you can potentially have a negative number. So I'll erase this. So since n is greater than or equal to big N, and big N is greater than the natural log of epsilon, natural log of r, by this chain of inequalities, it follows that little n is greater than the natural log of epsilon divided by the natural log of r. Or, since it follows that now the goal at this point is to make the r raised to the n be less than epsilon. So using our inequality, we can multiply both sides by ln of r. But be careful. Remember what we said about the ln of epsilon divided by ln of r. It could potentially be negative, especially when epsilon is greater than 1. And because we're multiplying both sides of the inequality by a negative number, the inequality sign must be flipped. So let's continue our proof. Multiplying both sides of the inequality by the natural logarithm of r and then flipping the sign, we get and now we could exponentiate both sides to get rid of the natural log, and notice that the n goes back to the exponent part of r. Now we could just simplify by getting rid of the natural log and the e to get our sequence is less than epsilon, which is basically what we wanted to show. So we can conclude by writing, therefore, the distance between the sequence and the limit of the sequence, which is equal to r raised to the n, is less than epsilon, which is what we wanted to show. And this concludes the proof for item A. Now let's take a look at item B. Notice that the only difference between the two items is the interval that r is found in. In item B, r is in the open interval between -1 and 0. In item A, r was in the open interval between 0 and 1. The proof for item B really follows the same steps that were taken in A, except that we need to take a closer look at our choice of big N. Our choice of big N for item A, remember, was Since we're told that this r is in the open interval between -1 and 0, all of which are negative quantities, let's direct our attention to the expression ln of r found inside of the greatest integer function, since it's really what we're concerned with. Let's also recall that the ln of r, where r is a real number, is only defined when r is greater than 0, meaning we cannot have r denote a negative number. If we quickly take a look at the graph of ln of r on the r and y axis, we see that we have an asymptote at r equals to 0, and ln of r crosses the r-axis at r equals to 1. So notice that our region that we're working with between -1 and the origin are undefined. So since we get to choose what big N is, what can we do to force our negative value r to be positive? Well, how about we enclose it with absolute value bars? That is, so this is our new N for the proof of B. Now let's quickly go over the proof of B. Since we said that B follows the same logical progression as A using the Epsilon-N definition, I've written out the proof so that I could just quickly guide you through it. So we could start by saying that let epsilon be greater than 0 be given. Define N to be the following, that choice of N we just saw before. Let N be greater than or equal to big N, be arbitrarily chosen. Then the distance between A of N, the sequence, and the limit of the sequence is equal to r raised to the n minus 0, and this is equal to r raised to the n. And notice that I'm taking the exponent n out of the absolute value bar, but I'm keeping the absolute value bars because, as we've said, r has to be a positive number. So since n is greater than or equal to big N, and big N is greater than the natural log of epsilon, the natural log of the absolute value of r, it follows that little n is greater than the natural log of epsilon divided by the natural log of the absolute value of r, because of through this chain of inequalities. Now, if we multiply both sides of the inequality by the natural log of the absolute value of r, our sign has to change. So now we can exponentiate both sides, and we get that this comes down and the epsilon comes down, and we get this inequality, which is really what we wanted to show. The absolute value raised to the n is less than epsilon. Therefore, the distance between the sequence and the limit of the sequence, which equals to r raised to the n, is equal to the absolute value of r raised to the n is less than epsilon, which is exactly what we wanted to show. I hope this video was helpful, and thank you for watching.